Hey, welcome back to Calculus. In this second day of section 6.4, we're going to continue to look at some work problems, problems where we have to kind of use the context of the problem to set up our local estimate so we know what integral we're looking at to calculate the work. All right, both of these problems are similar in nature. I want to show you how to set up an integral that you use to calculate the work for a lifting problem, lifting something whose weight is kind of changing as we lift it. And then I want to give you an example that's really the same kind of thing, but it's in the context of pumping a fluid out of something. Pumping a fluid out of something, well, basically you have to lift the fluid. So they're really the same kind of problem. Okay, so let's get going. Here's the example. It's from your text. You can check it out there if you prefer. But so we're going to look at a 200-pound cable. So this cable weighs 200 pounds total. It's 100 feet long, and it hangs vertically from the top of a tall building. And in particular, the building is more than 200 feet. So the picture is a nice graphic there. And then what's the question? The question is, well, how much work is required to lift the cable up to the top of the building? Okay, well, you might think like, well, it's 200-pound cable, 100 feet. Why don't we just not multiply 200 by 100 and get the work? Well, it's because you don't have to lift all 200 pounds that 100 feet, right? The only part of the cable that has to get lifted 100 feet is this point down here on the end. A little point on the cable here only looks like it has to get lifted about 25 feet and so on. So it's that as you lift the cable, the amount of weight is changing because you don't have to lift the part you've already lifted. So that's why we need an integral. Okay, so it's not a multiplication problem because the weight is changing as we lift the chain. So how are we going to do it? Well, the idea is let's just think about a small section of chain. Yeah, a little piece of it the author has in this figure drawn it, just this little piece here. How much does that little piece weigh? Well, the chain is 200 pounds, so it's 100 feet long, so it's linear density, if you like. It weighs 2 pounds per foot. So if you take a little piece of length delta x, that little piece weighs about 2 times delta x pounds, right? Because if you do the units, if you take 2 pounds per foot, then you multiply it by delta x feet, well, then you get the feet cancel and you get pounds. 2 times delta x pounds is how much that little piece of chain lifts. And if delta x is very small, then the amount that this piece of chain is lifted is approximately the same for all points on it. Yeah. What is that amount? Well, in the coordinate system over here, the author is calling it xi star. You can just think of it as an x value. You have to lift that piece of chain xi star feet. Yeah. So how far you have to lift it depends on what section of the chain. So you're taking something that weighs 2 times delta x pounds and you're lifting it, you're moving it a distance of xi feet. So your local estimate then for the work, I'm denoting it by wi just to match the author's notation here. The work to take this little ith section to the top of the building should be about 2 delta x, that's our force, times xi, that's our distance. So force times distance is work. I'm just rearranging that to make it look nicer. 2 times xi star times delta x foot-pounds. Add all of those local estimates up, you get a Riemann sum for the work. Take the limit of that Riemann sum as delta x goes to 0. This tells you what we're integrating. We should be integrating 2x dx. What are the limits of integration? Well, what are the extreme values of x? The smallest value of x is 0, and the largest value of x is 100. Okay, so pause the video and let that soak in, but it all boils down to, yeah, our work should be the integral from 0 to 100 of 2x dx. I'll leave it to you to check the details of this calculation here. The antiderivative of 2x is x squared. You evaluate that from 0 to 100 and you get 10,000, and one of the units on that, it's foot-pounds. 10,000 foot-pounds of work to lift that chain. Okay, cool. Little side question here. What if we're only going to lift the first half of the chain? Yeah, so going back to the building here, we're only going to take the top 50 feet and lift it. How could we compute the work? One way to think about that, there's different ways to approach this problem, but one way to think about that is you could just think, well, the bottom 50 feet of the chain is just some weight. How much is that weight? Well, at 2 pounds per foot, it's 50 feet of chain. It weighs 100 pounds. So you've just got 100 pounds of weight hanging on the bottom of that chain. That 100 pounds is going to get lifted 50 feet. If you pull the top 50 feet of the chain up, that 100 pounds, that bottom half of the chain gets lifted 50 feet. And so the work that you have to do there is 100 times 50. So I'm sort of setting this, I'm breaking this work up. Kind of thinking about the work on the top half and the work on the bottom half separately. And the bottom half isn't a calculus problem. You're lifting 100 pounds, 50 feet. It's 100 times 50 foot-pounds of work. The top half of the chain, it's just like the previous problem. The top half of the chain, well, you're not, as you lift it, its weight is decreasing. So by the same argument, you're going to integrate 2x dx, but you're going to do it just from 0 to 50 this time, because the largest value of x for the part that is moving, the part where the force is changing, is x equals 50. So you can check my computations here, but the integral from 0 to 50 of 2x dx is 2,500. Okay, 50 times 100 is 5,000, and you add those two things together, so it's just 7,500 foot-pounds to lift the thing 50 feet. Cool. So this is kind of a useful idea that even though this is some length of chain, in terms of the physics, I can just assume, well, this top 50 feet of chain has a 50-pound weight hanging, or excuse me, 100-pound weight hanging on it. And that 100-pound weight has to get lifted 50 feet. Okay, so that's 5,000 foot-pounds from that, plus the chain part. Nice. Okay, one more example. Taking this example and also the nice graphics from your book. This time we're going to be lifting some fluid, really, but the author calls it pumping it. Okay, so let's orient ourselves. We have a tank. It's in the shape of an inverted cone, so its vertex is shaped down. It's a huge cone. Its height is 10 meters, right? So that's a very large cone, and it has a base radius of 4 meters. Maybe it's something like a concrete plant or something like that. And it's filled with water, but not all the way. It's filled with water to just a height of 8 meters. Okay, so it has 2 meters of airspace on the top. And we want to find the work to empty the tank by pumping the water out and over the top. So we're going to pump the water out and over the top of this tank. So basically we have to lift it. We have to lift the water. And why is it a calculus problem? Well, because the volume of water that we have to lift, say a little slab like this at depth x in the author's coordinate system, x is going to go from 2 down to 10. And the volume of water depends on the depth. Yeah, and we also have to, just like in the chain problem, that volume of water is being lifted a different distance. So it's not just a multiplication problem, but we can think of this just like the chain problem. What we have to do is figure out, well, for a little thick slice here, so a vary x by delta x, we have to figure out how much water is there. What's the volume of that water at that slice? Because we can multiply that volume by the mass density and then times gravity to get how much it weighs. So this is kind of like the analog of our little piece of chain. How much does that weigh? As soon as we can figure out how much that little slab weighs, well, we multiply it by how far we're lifting it, and we integrate that. All right? So how are we going to figure out the volume of this little disk? Well, the volume of a disk is the area of its base, which is a circle of radius r sub I, times delta x. So what we really need to know is, what's this r sub I? We need this radius. We need the radius so that we can get the area, so that we can get the volume, so we can get the weight of that little slab, that purple slab. Okay, so the weight is the density times the volume. The density, we're told that water's density is 1,000 kilograms per cubic meter. We're going to multiply that by, sorry, I didn't leave myself units, room for the units, but we're going to multiply that by 9.8 meters per second squared. So 9,800 newtons is the density, the weight density of the water. So what we need is this volume piece. The volume of that thing, it's the volume of a circular cylinder, so it's just the area of its base times the thickness. The thickness is delta x, so I'm just repeating myself. We need this r sub I. How are we going to find it? we're going to use similar triangles. So cutting out of the picture there, this triangle, so you can see the height of the whole cone was 10 meters. I'm going to leave the units out of the conversation. The base radius was 4. And at that slab height, if we called this r sub I, well, that also is one leg of a right triangle. We took this depth at x sub I star, so the difference is 10 minus that. So using the principle of similar triangles, the ratio of this shorter leg to the longer leg, that is r sub I to 10 minus xi star, it has to be equal to the ratio in the other triangle of the shorter leg to the longer leg. It has to be equal to the ratio of 4 to 10. Yeah, or if you prefer, you can reduce that to 2 to 5. Do a little bit of algebra, solve that for r sub I by multiplying both sides by 10 minus xi star. Then the volume of that slab is pi times the radius squared, that's 2/5 times the quantity 10 minus xi star squared, times its thickness. I'll let you check the math. I won't try to pronounce it. I feel like my voice is going out from me there, but that's the volume of that slab. Right? So this quantity is what we need to multiply by that weight density, that 9,800 newtons per cubic meter, to get the weight of that slab in newtons. Okay, so the local estimate is the weight of the slab times the distance that we lifted. The weight of the slab, we said it's, well, gravity times the weight density of water times the volume of that slab, and then this is the distance. All right, so here, just to make this a little bit more clear, the weight of the slab is the quantity that I'm highlighting in yellow. The distance that we're lifting it is the quantity that I'm highlighted in green. So the summation of that, I don't have it written on the slide, but the summation of that would be our Riemann sum. We take the limit of that Riemann sum as delta x goes to 0, the number of subintervals goes to infinity, and we get an integral. And this quantity tells you what the integral is going to be. It's going to be, well, we have some constants, 9.8 times 1,000 times 4 pi over 25. Those will all go in front of the integral. And then we're integrating, what's it going to be? X times 10 minus x, oh, sorry, typo, squared, x times 10 minus x quantity squared dx. All right, let's look at the integral. Here I parked my constants out front. 9.8 times 1,000 is 9,800. Put the 4 pi over 25. Fixed my typo, x times 10 minus x quantity squared dx. And what are we integrating that from? Again, x went from not 0 to 10, but 2 to 10, because there were only 8 meters of water in this thing. So I didn't put in any details. I'm going to leave it as a little informal exercise to you to compute out this integral. As an exact fraction, it's that thing. It's about a little more than 3 million over 3 times pi joules, or as a decimal, about 3.36 million joules is the work to pump the fluid out of there. Okay, so I hope that was a useful example, and thanks for listening.